That brings us to 4.7, optimization. Optimization is a really cool unit. It's a pretty intense unit that has a lot of different pieces, kind of like related rates, but it's the first time we really get to experiment and play with everything we've learned so far this year, and actually everything we've learned until this year as well. What makes this super exciting to do is that you can actually have a job finding optimizational problems. You can work for a company and figure out how big or small Amazon boxes should be to use the least amount of material and save the most money. You could work for a chip packaging company to find out how much air should be in a bag to make as few chips as possible break. Optimization has a lot of really cool applications, and it's like for the first time we get to actually get a job using calculus. So optimization is the process of determining the best solution to a problem, the maximum amount of money or the minimum amount of material. So the way we're going to solve these problems, we always start by reading the problem a bunch of times until we understand it and we can identify the variables. Sounds a lot like related rates. I hope you feel like the same thing. The next thing we're going to do is assign symbols to represent the variables we have, and then draw and label a picture. Then we're going to figure out what are we looking for that needs to be maximized or minimized. And finally, we're going to find the absolute max and the absolute mins over the entire function. So on page 352, we're going to look at example 1. A farmer with 400 meters of fence is going to enclose a rectangular plot that borders a straight river. If the farmer does not fence the side along the river, what is the largest rectangular area that can be enclosed? So let's draw a picture before we start. Here's my river. Even make it blue. This is my blue river. And I'm going to enclose this land with the fence, and it's going to be a rectangle. And I don't need to enclose the fence along the river because I guess my animals don't swim, so they won't run away. Now I need to understand what question am I talking about. I'm looking at the largest rectangular area. So I need to know something about my area. And I want to find the maximum because I want the largest. So let's label. This will be my x and this will be my y. So my area is going to be x times y. Now they give me some more information. They tell me I have 4,000 meters of fencing. So that means my fence is going to go all the way around here to here to here. And hopefully when I did that highlighting, it helped you remind you that that means perimeter. So this piece is also x. So I know that my perimeter is 2x plus y, again, because I'm not fencing the side along the river. And they told me in my problem that that has to be 2,000. So take a second, please, and make sure that you understand where all of these pieces that came from. Okay, so I know that this is the quantity that I want to maximize. So this is the one I'm going to deal with first. I have 2x plus y is 2,000. I don't really want to have three different variables, area, x, and y, when I go to do my derivative. That's going to be quite a different rates problem. So instead, what I can do is solve for y, since nothing's moving. These are all static. So 2,000 minus 2x equals y. Now let's take that and plug it in for y. So my area is no longer x times y. It's going to be x times 2,000 minus 2x. So 2,000x minus 2x squared. Now if I want to find the maximum, I need to find the derivative and then find the maximum from there. So my derivative is going to be 2,000 minus 4x. We'll find our critical number by setting it equal to 0, and we get 4x equals 2,000. So x is going to be 500. Now let's see if that's a minimum or a maximum. Since we only have one critical number, it really better be a minimum. It better be a maximum because that's all I have. But we'll just test it to be sure. And I'm going to use my derivative right here that I'm going to be plugging into. So let's plug in 1. 2,000 minus 4 is going to be a positive number. And then let's plug in like 1,000. 4 times 1,000 is 4,000. 2,000 minus 4,000 is going to be a negative number. So if I increase and then decrease, yep, I have a maximum there. So now let's go back and make sure that I have read and answered the problem. If a farmer does not fence along the side of the river, it's the largest rectangular area that can be enclosed. So it didn't ask me for one side, which is what I found, 500. It wants the largest area. So first let's find y. And I get y is 2,000 minus 2 times 500, or my y is going to be 1,000. So the largest area that can be enclosed is 500 times 1,000. Oops. So 500,000. And let's see, that's going to be meters squared. Now in example 2, we're going to have a square sheet of sheet metal with 18 centimeters on either side. We're going to cut off a small square and turn up the edges to form an open box. What are the dimensions of the box? So we're looking for the dimensions of the box for the largest volume. So again, first we're going to do is draw it. So there's my piece of sheet metal. It's 18 from one end to the other, and on this side as well. Now we're going to cut these little squares out here, and then we're going to fold it up and make an open box. So it's going to be a square, so let's call it x by x. So now my inside pieces, let's do it another color, from here to here, if this is also x by x, is 18 minus 2x, and my inside piece from here to here is also 18 minus 2x. So volume is going to be length times width times height. Let's figure out what our length, our width, and our height are. Our length is 18 minus 2x. Our width is also 18 minus 2x. And our height is going to be how much of the box is turned up. So it's this piece, or just x. Now, since I only have one variable, I don't have x's and y's, this one equation is enough for me. Of course, I could do a product rule if I wanted to, or I could just distribute, do a little bit more work up front, and then use the power rule, which is what I'm definitely going to choose to do. So I have 324 minus 36x minus 36x plus 4x squared, and all of that is multiplied by x. So I have 324x minus 72x squared plus 4x cubed. That's my volume. I'll take the derivative of the volume, and I'm going to see if I get what I get for critical numbers and then what I get for my maximum. So my derivative is 324 minus 144x plus 12x squared. We'll set that equal to 0, and first thing I'm going to try to do is factor out a 12 out of each piece. So I'm going to have 12 times x squared minus 12x plus 27. And then let's break it into two groups of parentheses. So if I have a minus 9 and a minus 3, I'm going to get a minus 12 and a positive 27. So my critical numbers are x equals 9 and x equals 3. Now it's asking us for the absolute maximum, so I need to take into account the smallest and the largest number possible as well. The smallest number that I could ever have for my x would be 0. And the largest number would be 18, because that's as large as my sheet metal is. So let's find our absolute by setting up our XY table. And we're going to be looking for the volume. So we have 0, 3, 9, and 18. So when I plug in 0, my volume's 0. I'm going to be plugging in volume just for reference, into this one. When x is 3, my volume is 432. And again, I'm just plugging this back into my original volume. When x is 9, my volume is 0. And when x is 18, my volume is 5. I made a mistake. Of course it can't be 18 because we have x's on either side. So we actually only go to 9. So we can see our maximum is at x equals 3 and my volume is 432. So let's make sure we answer the question. What are the dimensions of the box? So the box should be 3 centimeters by 3 centimeters. And that will get us the largest volume. Let's step into the world of manufacturing with example 4 on page 354. A manufacturer needs to produce a cylindrical container with a capacity of 100 centimeters squared. I think that's supposed to be centimeters cubed. The top and bottom container are made from a material that costs 0.5 centimeters per centimeter squared, and the sides are made from something that costs 3 cents per centimeter squared. Find the dimensions that will minimize the company's cost of producing the container. So let's first show a picture of what we're talking about. We have this cylinder. So I'm going to be thinking about a volume of my cylinder. Here's my radius, and here's my height. So the volume of a cylinder is pi r squared times the height. Now I need to think about making the product. That's going to be my surface area. So if I was to unroll this cylinder, I would have a rectangle and 2 circles, one on the top and one on the bottom for my top and my bottom, my lid and my bottom. So my radiuses are here. Those are the same radiuses, and my height is still my height. But I'm not sure if you remember this. If I was to roll out that circle to make this, so if I'm going to roll out this circle to make this, it's actually the circumference of the circle. So it's 2 pi times the radius. So to find the surface area, I have 2 pi times the radius times the height plus the 2 circles for the lid and the bottom. That's going to be the area of both of those, 2 pi r squared. Now we're trying to minimize our cost. So let's make our cost function. The cost function is going to be, for the body of the material, it's going to cost 3 cents. So it's 3 cents times 2 pi r times h plus, and then 5 cents for the lid and the bottom, 2 pi times r squared. So this is the function that I'm trying to minimize. I'm just going to write minimize here. I can see in this function I have 2 variables that I need to deal with, my radius and my height. In this one I only have radius. If I can simplify my volume to get away from height, that will make this problem a lot easier and not quite a related rate partial differential equation. So my volume is going to be 1,000 pi r squared times the height. So if I isolate my height variable, it's 1,000 over pi r squared. And now I can substitute that into my cost. So I have 3.3 times 2, so 6 cents, times pi times r, and then 1,000 over pi r squared. We'll come back and simplify that in 1 second. And then 10 cents times pi r squared. So my pi's will cancel and 1 r will cancel. And I'm still left with 1 r in the denominator. So I'm going to write that as 60 over r plus 10 cents pi r squared. And since I will be finding the derivative of this, it will be much easier for me to rewrite this as 60 times r to the negative 1. So our next step in order on the path to find the min or the max is to take the derivative. So we have the derivative of the cost is going to be negative 60 over r squared plus, and then we're going to have 20 pi r. Now, again, we want to know when our derivative equals 0 and when our derivative does not exist. So we're going to need to make a common denominator for this. So negative 60 plus 20 pi r cubed all over r squared. So what I did there was made a common denominator. I multiplied my numerator by r squared and my denominator by r squared. And then once they were all r squareds in the denominators, I was able to combine my numerators together. And now we'll set my numerator equal to 0 and then my denominator equal to 0. So negative 60 plus 0.20 pi r cubed equals 0 and r squared equals 0. So we can have a radius of 0, which doesn't really make a ton of sense. That wouldn't really be a cylinder. Or we could have a radius of, let's see, 0.20 pi r cubed equals 60. 60 over 0.20 pi. Then r will be the cubed root of 60 over 20 pi, which is about 4.571 centimeters. Now my radius, all right, we again should just make sure that we have a max here, which hopefully we do since it's our only critical number, 4.571. And if I plug in to my derivative, let's say 1, I'm going to have negative plus a small positive, which will be a negative. And if I have, let's say 5, that'll be a positive over a positive. So yep, we have a min. So that's good. Now the question didn't want to know the minimum radius though. It wanted to know the dimensions that will give the company the minimum cost for the container. So we know that our radius, switch colors here. So we're going to know that our radius is 4.571 centimeters. Now we need our height. So 1,000 over pi times 4.571 squared. And I get 15.236 centimeters. So those are the smallest dimensions that will cause, those dimensions will cause the smallest cost for making this container. Example 5 on page 355 is kind of deceiving. It has just a few words, but it's packed with a lot of information. A rectangle is inscribed in a semicircle with a radius of 2. Let's draw that. So we're inscribed in a semicircle with a radius of 2. So there's my semicircle. Here's my r equals 2. And we have a rectangle that's inscribed in it. Find the dimensions of the rectangle that have the maximum area. So first thing I need to do is start labeling these pieces. This is my rectangle. These are my y values, my x, and then since I also go into the negative direction, that's my x and that's my y. So to find the area, so my length is actually going to be 2x and my width is going to be just y. So my area is 2x times y. Now I'm not sure if you can recall the formula for a circle, but in this case our formula is going to be x squared plus y squared equals 4. The formula for a circle is x minus h squared plus y minus k squared equals the radius squared, where h and k are my center and r is my radius. So that's where I'm getting this equation from, the second equation. So we're going to solve it for y, so we can substitute into our original that they're giving us. So y squared is 4 minus x squared, or y equals the square root of 4 minus x squared. I'm not worrying about the negative square root because I'm only looking at a semicircle, so I don't need to worry about the negative part of my circle down here because the circle doesn't extend that far, it's just a semicircle. Okay, so now let's plug into my area. My area equals 2x times the square root of 4 minus x squared. So this is definitely going to be a product rule, and when I write that out, I'm going to be sure that I rewrite 4 minus x squared to the 1/2. my u prime will be 2, and my v prime is 1/2 times 4 minus x squared to the negative 1/2 times negative 2x. So we can simplify this some more. My derivative is going to be 2 times the square root of 4 minus x squared, and then minus x squared over, minus 2x squared over the square root of 4 minus x squared. So let's see, I simplified, I canceled that one and got a negative 1 and that 2. And then I have negative 1 times positive 2 is negative 2, and x times x is x squared. So now, in order to simplify this equation, I need to multiply both the numerator and the denominator by square root of 4 minus x squared in order to have a common denominator, and then I can simplify my numerators. So my area is going to be 2 times 4 minus x squared minus 2x squared all over the square root of 4 minus x squared. So that's 8 minus 2x squared minus 2x squared all over square root of 4 minus x squared, or 8 minus 4x squared all over the square root of 4 minus x squared. So now I'm going to take my numerator and my denominator and set them equal to 0 to find out either when my derivative doesn't exist or when my derivative equals 0. So to identify my critical numbers. So we have x squared equals 2. So the square root of 2. And I'm not going to worry about x being a negative square root of 2 because I can't have a negative length of a rectangle. And then my other one could be 4 minus x squared is 0. So x is going to be 4, x is 2. And now let's take a look at what my length of my, what the dimensions could be. The smallest rectangle I could have would be a 0, and the largest would be 2 for my x because that's my radius. So to find our absolute max and our absolute min, but this time we're looking for our absolute maximum, we're going to set up our xy table and look at the area formula. So when my x value is 0, my area is going to be 0, and same with when my x value is 2, my area is also 0. So where I'm concerned is my x value at square root of 2. So let's first find out what my y value is at square root of 2. So y is the square root of 4 minus square root of 2 squared. So that's square root of 4 minus 2, or the square root of 2. So my y is square root of 2 and my x is square root of 2. So my area is 2 times square root of 2 times square root of 2. So that'll be 4, and that is definitely my maximum. So find the dimensions of the rectangle. The rectangle is going to be square root of 2 by square root of 2 plus square root of 2, 2 square roots of 2. Because remember, our x is twice long as our y.